Hey guys, so today we're going to be working on the gases section of the Regents chemistry curriculum.
This is Aleko. I'm Suhana. Nabiha couldn't be here today, but she's with us in spirit. So we're going to start off by describing the properties of gases.
So gases, underneath the broader term of expansion, it's that gases move rapidly in all directions, and given the name, they expand to fit any container that they're in. That's why gases have no definite shape or volume, because they just expand to fill whatever space. So if you were to put a gas in the 2-liter container and seal it off, then the volume of the gas at that point would be 2 liters.
And gases are like liquids. They flow. They also have low density, and they're compressible. They're spaced out apart such that the volume of the gas is mostly empty space. They also effuse and diffuse.
Now, diffusion is used to describe when different gases mix due to the random particle motions that they have. Now, the rate of diffusion depends on the kinetic energy, the size, and attraction of the particles. Effusion is a slightly different process of when gases leak from a container through a very small opening into an empty space. For an example would be a tire leaking air. So, as Suhana is drawing now currently, there's the tire, the orange dot is meant to represent the hole, and the little lines are meant to represent the air coming out of it. So, with the process of effusion, there are different rates of it, and the rate of it would increase based on the rate of it would change based on the size of the particle. For example, the rate would be faster if you had a smaller particle like helium or hydrogen.
And noble gases.
That too. Small ones.
I have a noble gas joke.
Do tell.
Sometimes I miss noble gases when they are gone.
Riveting.
You guys also need to be familiar with the KMT, the kinetic molecular theory. What you need to know is that particles of an ideal gas have elastic collisions with each other. They move in constant straight line motion. Their average kinetic energy is directly related to their Kelvin temperature. And the volume of ideal gas particles are negligible, as the distance between them are very large compared to their sizes. They also have no attractive forces between them, much like Aleko and his past relationships.
You didn't need to say that, but whatever. So, sadly, life can't be ideal. So, here are the differences between real gases and ideal gases. So real gases obviously do not follow the postulates or the rules that ideal gases follow. So one of them being that there are attractive forces between the gas molecules, given the fact now these attractive forces do make a difference in a multitude of variables, and although gases are real gases, there are those that act a lot like ideal gases, and those would be hydrogen and helium and small noble gases, given the fact that they have very small atoms, and because they're small, they have very weak forces of attraction. They also behave most like an ideal gas under low pressure and high temperature, mainly because low pressure means they're far apart and the forces between them are minimal, and the high kinetic energy just allows them to move faster.
Here are your gas law equations. You need to be familiar with Boyle's law. This deals with pressure and volume. Just know that this is an indirect relationship. As one increases, the other will decrease. Gay-Lussac's law deals with changes in pressure and temperature. That's a direct relationship. Charles' law deals with volume and temperature, also a direct relationship. And they all combine to form the
combined gas law equation. I'm sorry, I was thinking about ideal gases. But all three of these equations are derived from the combined gas law equation. So even if you forget one of these individual three, you can still remember the combined gas law equation and be able to solve most, if not all, the problems that they throw at you.
So it's time to practice.
So a container at 273 Kelvin containing 2 liters of gas is heated up to 350 Kelvin. what is the new volume of the gas assuming pressure remains constant?
Pause the video now and work on it on your own. But here's a little hint. It deals with Charles' law. And welcome back. Now that you've worked on it on your own, we're here to help you. So the setup for Charles' law would be V1 over T1 equals V2 over T2. You know you're not going to take pressure into account because the problem said pressure remains constant. So we don't have to worry about that.
So the numerical setup would be the 2 liters over 273 is equal to V2 over 350.
Now the only reason we're not using units is just to save space, but you guys should always be using units in your problems. After you do the math, your new volume should come out to about 2.6 liters. If you got it right, congratulations.
So next up, we have a gas with a volume of 6 liters has a pressure of 2 atmospheres. If the volume were to decrease to 3 liters, sorry about that, what would be the new pressure of the gas if the temperature remained constant?
Pause the video and work on it on your own. Now that you've worked on it on your own, we're back to help you through it. So since temperature remained constant, we're just going to be dealing with pressure and volume, and that is Boyle's law. So here is Boyle's law. P1 times V1 equals P2 times V2.
So given this, your numerical setup would be 2 atmospheres times 6 liters is equal to 3 liters times P2. Again, we're not writing units just to save space, but on the exams and everything, make sure you write units because they're very important.
After you do your math, you should see that P2 equals 4 atmospheres. It's a big A.
It's a very big A, but don't worry.
This makes sense because your volume decreased, and so you know your pressure is going to increase because it's an indirect relationship. You got it right. Good job.
Now, since practice makes perfect, here's one more problem. If a gas has a pressure of 2 atmospheres at 300 Kelvin, what would be the new temperature if the pressure increased to 4 atmospheres while volume remained constant?
Pause the video. Work on it. Welcome back. Now we're going to go over it with you. And now, you see volume remains constant. And what formula are we going to use?
Gay-Lussac's formula.
And this is Gay-Lussac's formula. P1 over T1 equals P2 over T2.
So, your numerical setup would be 2 atmospheres over 300 Kelvin is equal to 4 atmospheres over T2.
Once you do the math, you see that T2 is equal to 600 Kelvin.
Which makes sense since pressure and temperature have a direct relationship. One increases, the other one does as well.
Last problem.
So, this one is a bit more complex, but it's not that hard. At a temperature of 273 Kelvin, a 400 milliliter gas sample has a pressure of 101.3 kilopascals. If the pressure is changed to 50.65 kilopascals, at what temperature will this gas sample have at a volume of 551 milliliters?
Pause the video and work on this on your own, but don't let the units scare you. Now we're back. So, you should know that you're going to be using the combined gas law because nothing remained constant in this equation. Your combined gas law looks something like this.
Looks exactly like
Yep.
So, Combined gas law, P1 times V1 over T1 is equal to P2 times V2 over T2.
And when you plug in your numbers,
sorry, just gonna have to. So you get that. Gonna have to erase it for more space because these numbers are a little tricky. You get 101.3 times 400 milliliters over 273 is equal to 50.65 times 551. It's a very bad, I have bad handwriting, but it's fine. Divided by T2, since that's what you're looking for.
now when you do the math, you should get that T2 is about 188 Kelvin.
If you got it right, then congratulations.
Now we're going to talk about STP. This is your table A on your reference table. Under standard conditions, we can compare substances to one another. Standard pressure is 101.3 kilopascals, or 1 atmosphere, or 760 millimeters of mercury. Standard temperature is 273 Kelvin and 0 degrees Celsius. You thought that was the last problem, but here I am with another one.
Yep. So the problem would be a 2-liter sample of gas has a pressure of 650 millimeters of mercury at a temperature of 298 Kelvin. What would be its new volume at STP?
Now put your skills to work and pause the video. Work on this on your own. We're back. Now, you should know you had to use the combined gas law. Here is your gas law.
It's important to remember these equations because if I remember correctly, these are not on your reference table, so it's good to remember this just because it's a very vital part for the Regents. So when you plug in the correct values, you would get 2 times 650 divided by 298 is equal to...
What's your STP, Aleko?
So your STP would be 760 times the volume that you're looking for, that's supposed to be a V, divided by your standard temperature, which is 273.
Now when you do the math, your new volume should be about 1.6 liters.
Yep.
And there you go. You're done.
Yep, that's pretty much all there is to gases. It's a short topic, so good luck on your Regents, guys.
Science.